So these two items is hash set, a hash map. So here we have all the alphabets, and then here we have the number of occurrence, right? So the thing, the moment you create this, say you do a for loop inside somewhere, and you check for every single alphabet, say for C, that then you go through the S stack and the T stack, whether are they equal or not. So that means you are checking whether the frequency for C, is it the same for the S stack and the T stack, and if they are the same, that means it's an anagram. If it's not, they are not anagram. You kind of rinse and repeat for every single alphabet per se, and then you run through the entire alphabet list, and if every single thing is the same, it is an anagram. The main properties is that we do create two separate hash maps for two separate words. So you have hash map 1, hash map 2. So say for hash map 1, A, you got how many alphabets? About 3. N, you got how many alphabets? You have 1. G, you have how many alphabets? 1. So it's simply saying that for each of the alphabets that's stored in that string, so how many alphabets are there? And the number of frequency for each. You rinse and repeat for the other string. And the tricky part, in my opinion, is on how do you am able to check for the alphabet and the frequency for both string. So I mean first and foremost they follow the same format, right? So I think one thing I will say is that in the for loop, I will indicate the alphabet for this. So each time I go through the alphabet, we are technically entering into the realm of stack 1 and stack 2. And the only difference will be the frequency that we are checking, right? And so we want to check that for both the frequency for S and T, are they equal or not? And then the loop, right, it will go through every single alphabet. And every single alphabet, they're gonna check like if the frequency is similar or not. In any cases that is not, it will just loop out and say it's false. But if it's an anagram, it definitely for every single alphabet, all the frequency will share the same for both the S and the T. And then it will return true as being like an anagram. And then we have solution 2. It just sort the value. So you have the 1 and the 2, right? You sort all of them. And they supposedly will be arranged to become identical to each other, right? Because for anagram, the feature is that they have similar alphabet and same number quantity. And if that's the case, if you sort these two strings, they should become two strings, like become a string that is identical. And when that happens, what you really need to do is just do a equal checker to say that they are identical. So what you really have to do over here was that the thing is that the space complexity and then the time complexity for creating this sorting thing, right? it's n log n, and for some reason they say sometimes n squared. But I think what we really want to actually focus on was about the logic of this. So let me explain again. 1 and 2, if, okay, before that, let's tell ourselves what is the feature of anagram. Anagram is where you have similar alphabets, similar frequency, but doesn't necessarily that they are arranged properly. And then for this case, we do know that one of the feature that make anagram really hard to actually identify is because they are all jumbled up, or the alphabets are jumbled up. And we bring in this sorting feature into it and apply to both of it. You are technically removing the jumbled upness, and they will look immediately identical with one another. And first and foremost, it's very easy to tell that they are then identical. So once you sort 1 and 2, do a checker if they are equal, and if that's true, that will be an anagram. So that's pretty much it. I think there wasn't like, there's only solution 1 and solution 2 per se. So there you have it. Everything comes to an end.